you see my screen?
Yes. Are you going to turn on the camera?
Oh, sure. No problem. Yeah.
Are you talking? Are you muted?
Yes. Should we start right now?
Yes, go ahead.
Okay. Hello, everyone. Today, I will discuss some our technology advancement about the AI networking, especially on the RDMA and also TCP/IP. Of course, today we will also discuss the difference between the scale up or scale out and scale up networking. So first of all, let's talk about why people care about the AI networking today. Actually, the reason is, of course, the obvious reason that we just said that the computing power has increased like 1,000 times in the past 8 years. But if we look in detail about what is really changing in the past 8 years, is not because of one single chip they increased for like 1,000 times. Of course, a lot of people can do that. Actually, the reason that the AI computing power has increased 1,000 times because the definition of the AI computing from the single card to a rack of computer. Like I think in 8 years, when people talk about the GPU, talk about like AI computing, always refer to a card, like standard PCIe card. But about like 4 or 5 years ago, when people introduced the GPU, they said, okay, the GPU actually is made of like 8 chips, like a single module with 8 GPU inside. But until last year, the Jason Huang said, no, the supercomputer actually is a rack. The whole rack is a GPU. That's why he said the GPU is not big enough. They need a more bigger GPU. Actually, behind this, the reason why the definition of the GPU computing changed is because of interconnections across the GPU that changed. So that's why actually the reason the computing power of the GPU changed for like 1,000 times is that the computing, the link. So when we go back to see what the link it is, the link they compose like 2 parts. I mean, in the very beginning, when we talk about the networking, we talk about the link. We always refer to the TCP/IP. TCP/IP is very good. They designed for the connection for the different servers, but in the AI computing, because of TCP/IP, they have some like drawbacks because they designed for the wide range computing. People come out with like RDMA. The RDMA said, okay, let's go bypass the kernel because most of the TCP/IP, because of the kernel management, the speed and the latency is high, and speed is not that good. So they come up with the RDMA technology. The RDMA technology is very simple and very straightforward. They just bypass the kernel. When kernel is a problem, then we just get rid of the kernel. We just bypass kernel. We can send the data from the NIC directly to the application. The application can manage the data flow efficiently. That's why RDMA is one of the best protocol for the AI computing in the past several years. And in the open source community said, okay, because RDMA is it's proprietary to the NVIDIA. So why let's do like RDMA over the Ethernet? So we call it ROCE. And nowadays it's called the Ultra Ethernet. They want to use the RDMA technology inside the Ethernet. But this is for the protocol. When we go to see the link, not just the protocol to change from TCP/IP to the protocol like RDMA or like ROCE or UEC, but actually another fundamental change is about link. The link, when we talk about TCP/IP, we normally do not refer what kind of link it is, because people by default think about the link is MAC, like Ethernet. But NVIDIA said that, okay, when we want to make a super fast AI networking, we do not need only to change the protocol for the networking layer, but we also to update the link. Then they call it the NVLink, or we call it the future link. NVLink is based on the PCIe, and then they promote a very simple protocol on top of the link. Okay, I will talk about that later. And accordingly, for the open source and the community said, okay, NVLink, is NVLink is belong to NVIDIA. Why we do not, why not we us together, we can get like a CXL, like Computing Express Link to do that. I mean, even today, as this year, people think the CXL is still too heavy in the AI networking. Then they introduced called the AI link, ultra accelerator, the accelerator link. So our vision that in the change in the both protocol and also the link, our vision that we want to build up a high performance and low latency scale up cluster. So what is the scale up networking? This is about the word. Every people doing the AI infrastructure, they're talking about that. But actually in the old days, there is nothing called scale up networking. When in the past, we divided the connection in the computer system, like a CPU to CPU, CPU to device, and device to device. And of course, the device to device across some nodes, and node to node, and cloud to cloud. So for these 6 different connections, people have different technology. They develop like Intel has the UPI, and also AMD HT, and also ARM like CCIX. And for the CPU to device, normally people use like PCIe as a standard. And the device to device, they call it the PCIe P2P. And some like a TCP/IP, as we mentioned, and also RDMA. So when NVIDIA revolutionized this area, they introduced like an NVLink for, originally they introduced the NVLink is for the device to device connection inside the box. We call it because that's why they call it the bus protocol. And of course, they extended that into the device to device across the different board. And recently, they introduced the NVLink C2C. They want to cover the CPU to the device. So what is the scale up? So in the old days, we call that the out of a box connection, like a load to load connection, we call it scale out domain. So scale out means we add more server and then we have more performance. That's the very basic and also the principle for the scale out domain. So actually, when we talk about the scale up domain in the computing architecture, we always talk about the CPU performance. We talk about that CPU to CPU, like a dual way, like a quadral way, and even like an octal way. Like you put 2 CPU together, put 4 CPU together, and even for 8 CPU together. But in old days, actually, when we talk about the CPU and the GPU to like a NIC, we call heterogeneous computing domain. So you can see that in the old days, scale up networking actually is for homogeneous computing inside the CPU or between the CPU or among the CPUs. So NVIDIA just used this definition. They said, okay, so NVLink, why is it called NVLink? It's a scale up network because originally NVLink is only used for GPU to GPU connection. So the thing is homogeneous and also it's a computing unit. So that's why it's called a scale up. So actually you can think about that. We can think about that right now that the scale up networking is for the homogeneous computing across the GPUs. So that's a lot of people that are doing right now. And that's why we come up with this definition. So why the big model, like a large language model, they need to scale up networking? As in today's talk, people talk about the PP, PD, DP, PP, and also like TP. In different parallelism algorithm, we always need to scatter the data across different GPU, and then we do the computing. So in nature, when you distribute the data across the GPUs, you need communication. And the communication in nature is synchronized, they're not parallel, because you have to send the data 1 byte by 1 byte. Of course, use like a PP algorithm, you can let the networking to parallelize by itself, but still between the one GPU to another GPU is still serialized. So that's why, due to this data movement, the scaling of the computing across the GPU is very sensitive to the latency and also the throughput. That's why we need a scale-up networking. But actually, the key for the scale-up is dropping the leak. Why we say that? So originally, when we want to move the data from one GPU to another GPU, we need to use a PCIe switch and also a NIC, like a network adapter. The data will move from the GPU through the PCIe switch to the NIC, and the NIC send the data to another NIC, and then the NIC send the data to the GPU. So of course, you have a lot of technology to optimize this data transfer. So, but in summary, we need a CPU, we need a PCIe switch and with a NIC to scale out networking. But for the scale up networking, if you look very closely into the the infrastructure for the GPU like clusters, you can see the data movement is from one GPU to the UALink switch, and then UALink switch to another GPU. So you can see actually the UALink switch has the same position as a PCIe switch in the traditional way, like in the traditional scale out way. The only thing we drop is the NIC, or you can think about the NIC inside the GPU. But in either way, the network adapter, it doesn't matter, it's a ROCE network adapter, or it's like RDMA, it's IB network, or the traditional NIC, they just dropped. So in our definition, actually, when we talk about the scale up and the scale out, the difference is whether we use NIC or not. That is what we have in our definition. Actually, LFH leads the trends. 2 years ago, I think we did something, but we do call it scale up. We call it scale in. The reason because the scale up network, they only suitable for the small clusters. And I think in the white paper we said that the networking shift, the networking innovation, they shift from the port density. The port density is one of the big key value for the networking in the old days, because they want to scale out. Scale out means you need more port, right? So the port density is very important. But actually, in the recently, especially for the AI computing, like a rack scale computing, the scaling is not an issue, because you cannot put 1,000 computers inside one rack. Instead, you can only put like 32 servers, for maximum like 64 servers inside one rack. So when port density is not the critical issue or critical point we need to consider, then what we need to consider is the link type, and also the protocol on the link type to increase that. So actually, we do share the vision like 2 years ago. So, but we call it scale in. Scale up is better. It's really a good word compared to the scale in. So let's go back to the technology. Actually, the technology is correct. How to extending the PCIe transportation. So as I said, in the scale out and the scale in, so doesn't matter what kind of the link it is. Actually, they're all based on the PCIe. Then the real factor, the difference between these two kind of technology is whether you have an adapter or have a network adapter. So when we talk about the PCIe transaction, we talk about PCIe transportation. We always need a translator, like a PCIe to network translator, to translate the data from the CPU to the networking. But why just connect them together? Just connect the PCIe physical layer, like 30s to 30s, through a networking. So this is a very similar technology compared to the UALink. Actually, UALink is doing exactly the same. So our answer to the difference between the scale out and the scale up, actually, we think they're the same. The only thing difference is that the connection model, they changed. They changed from you need a protocol translator from the PCIe protocol to the Ethernet protocol by a network adapter, or right now you just connect them together. So we call it PCIe network. Of course, you can say CXL network or like an UALink network, or in the future, maybe like a UALink network, but they're the same. So let's revisit why we can do that and why people build up the, UALink built up the protocol based on PCIe, UALink based off the network based on the PCIe, and also the CXL based on the link based on the PCIe as well. The reason that people want to drop the Ethernet is because in the future, in the old days, because the Ethernet they designs like a layer by layer. In the hardware layer, they only standardize the DMA and the MAC. So that said, okay, the MAC serve like a data transfer, but they do not control whether the data reach the other MAC, like reach the destination. They just say, hey, I get the data from the upper layer, like the CPU, like the application, and then we drop the data into my port. That's it. So whether the data transfer from my Mac to another Mac or to the destination Mac, I don't care. Who cares? The protocol cares. Who runs the protocol? Actually, it's the CPU. It's the application, like a socket, like a TCP IP or UDP. Then in UDP and the TCP, you have a lot of mechanisms to control the data reach the destination. So actually, people know that in like 30 years ago and 40 years ago. So that's why they have two protocols. One protocol is UDP, say, hey, I don't care. If you want to care about whether the data reach the destination, you just need to program control by your application. The TCP said, oh, no, that's too risky. I will do the control mechanism by myself. So TCP introduced a shift window, like a window to guarantee the data can reach the destination. However, you see, actually all the innovations right now based on the Ethernet, they choose different ways. One said, okay, I just treat the Ethernet as a link. We just treat we do our flow control in our application. So I think Tesla, they introduced like a very efficient protocol based on the UDP to do this way. So that's okay. I only use UDP as adapter to send the data. I do the control by myself. And another way, like IWAP, I use TCP to do that. Either way, that's only the difference between the innovation in the Ethernet that you have to control the flow by the software, and all the software is runs in the CPU. So that's why they consumed a lot of the CPU cores in the Ethernet protocol. And for the PCIe, they're different. The PCIe, they introduce a logic layer. So this logic layer actually have a very strong echo mechanism. That's that whenever I send a data from my PCIe service to another PCIe service, I need to guarantee you reach it. In how can I say? When you do this, of course, the data transfer is very reliable. Very reliable. You can always receive. But the problem that you need to echo every time. You need to echo, say, hey, when I send one data, I say, hey, do you receive the data? When I check you receive the data, I send the next data. So the latency actually is a little bit longer, but because it's doing by the hardware, you cannot notice that. And because of the hardware to guarantee that data can reach to the destination, so the software is very simple. Normally people ask me that, what is the driver for the PCIe? So actually, this is a very, very, very good question. So when we think about the kernel, what is really the driver for the PCIe? It's not the PCIe driver by the different windows, okay? Actually, the PCIe driver is the memory address. It's a memory addressing. So like a star. Actually, the only driver in the PCIe system is we call the read L, like read W, like a read, like a star to fetch the data. So in other words, that in the PCIe technology, the CPU only see the device as a memory. They do not care about how you send the data. They only care about I can fetch a data from the controller. That's it. So you can see the PCIe and the Ethernet, they are different by design. The design is just how to control the data flow. So right now, some people think about that Ethernet with some like very, how can I say, very clever flow control is a good way. And some people said, oh, we just dropped the PCIe. We just dropped the Ethernet protocol. We just use our PCIe. We use memory addressing. So actually, that's why people discuss the difference between the scale up and the scale out. They always just said, oh, load and store. They said, in the Ethernet, you use the send and the receive. In the PCIe or in the UALink, you use load and store. Actually, in our idea, load and store and send and receive, actually, that's the same. The only difference that who will do that is the CPU do that or the controller, hardware controller doing that. So why in the CUDA, like GPU computing, like AI computing, we prefer the PCIe, not the Ethernet? The reason, as I said, because in the Ethernet protocol, the CPU need to do a lot of work. If you connect the Ethernet directly to the GPU, then the GPU core need to do that. So, if we choose the MAC, like choose the Ethernet protocol to do the GPU transfer, data transfer, you will see a lot of the CUDA cores, a lot of like the GPU cores, they're doing the data processing, just like a CPU, Then you will see the efficiency for the GPU cores to do the computing actually is much fewer than the PCIe one. Because PCIe, the GPU, they do not need to actually do not even need to care about the data transfer. They just say, hey, the PCIe controller give you the data. Then the controller give you the data. That's it. The only thing you need to see is you need to wait for the data achieved or arrive, or you just go to do another work and then go back. Then that's we summarize that. Because of the lightweight driver layer in the PCIe, that's why people prefer the PCIe in the CUDA, like in the GPU cluster, like also all called scale out. Then, so we talk about the link in the hardware layer. Then we talk about like the protocol in the software layer. In the software layer, besides the TCP/IP, we always think about to the application. What exactly the application want? Do the application need to know the TCP/IP? Need to know the socket? Need to know the send and receive? Actually, no. The application only want to know I want to receive the data from some memory address. That's I said. In the scale out and scale up networking architecture, we need to solve one problem. We need to let the application to know, we want to let the application to see the data just like the memory addressing. We do not need the application to know how the data arrived. So that's why we develop a software to hide all the data movement based on this kind of philosophy, and also we introduce I will talk about later, our software layer. So actually this is what we are doing in the originally, this is the HPC. HPC doing that. When we do the HPC, we hide all the data movement is MPI. In MPI, you do not need to know where is the data. You only need to see, I want the data and I want the data to, I want the data and the wait, or I want data to not wait. That's it. So in the HPC, actually, they do that before. So large language model is in between the HPC and the cloud native or the storage native, the protocol. So also, as I said, in the mainstream hardware, so you need to think about what we choose the Ethernet or choose the RDMA. That's it. So we promote our protocol. As I said, we talk about the protocol. We talk about the protocol in the software, and also we talk about the protocol in the hardware. So if we put it together, so we think about that RDMA over the CXL is one of the, I think it's the only way right now, or maybe in the future to have another alternative. But right now, it's a very good candidate to replace the RDMA and UALink. The reason we have three, we compare with the RDMA from the original IB and also Rocky from the link. As I said, with the RDMA over CXL technology or like PCI technology, you do not need the link. You do not need the adapter. That's a very key difference between the scale out and the scale up. And also, you only introduce a very thin driver layer. You do not need to take the TCP/IP protocol into the software or into the hardware. So the key feature with the RDMA over CXL that we based on the CXL technology. Actually, we based on the PCIe technology. It offers very low cost and high performance, and it's feature oriented because in the future we think the CXL will replace the PCIe very soon. So in the data flow, compared to the RDMA data transportation that I said, the data will move from the kernel space to the hardware and then go to another hardware. In the CXL data transfer, we just integrate the DMA from the NIC into the CXL switch because each PCIe have a DMA assigned with it. So that is what I said, scale up. So you need to drop the NIC. And we do not need to use the data copy. We only need data copy once, actually twice, okay, because through the switch. And then we do not need to take about the interrupts because it's a memory connection, so you can copy to the memory directly. And also, the CPU do not need to get involved. So combining the characteristic of IB and the PCIe technology, very similar to the UALink technology, the CXL with RDMA will provide a very low latency, high throughput, active and passive data transfer. The active means you need to wait. The passive means you do not need to wait. You just you can go back. So with the technology, with the CXL, so what is the new part is doing? Actually, new part is we have 3 layers. So the first layer is the CXL controller. We use the traditional one or like standard one. You can use like a PCIe with a DMA. And then the new part core will control or management all the PCIe CXL controller, and then to provide a unified memory address space to the LUPA lib. LUPA lib, they call the LUPA IB. They will provide like an IB device for people to use the IB, or you can use the user space UIO to program it directly. So we call it a unified protocol for the networking. So this is our reference design with FPGA to mimic the to provide the ASIC to provide the protocol, and then we use RDMA to link the different nodes. So similar to the UALink and also the app technology, we can have like a cluster, we can put in the rack. We have like 16 servers, and then connect with 2 switches. And then we can provide like an all-in-one server for the storage scenario. And for the GPU, because GPU need more bandwidth, then you can have more. You can stack the switch. You have like a 4, maybe like 8, if it depends on the GPU. Then you can put all the GPU like a slice into the cluster. So just like the rack scale. So for this reference design, there is no IB card needed, and also no Rocky card needed. But still, you have RDMA across the class, the rack, and all the server they have a global memory addressing across the GPU and also CPU. So the CPU, GPUs have the same memory addressing. The only difference is that you need to receive the data until to wait or not wait until the data arrives. So that we call the passive and active data transfer, and then we only need the network adapter when you want to connect to the clients, like you want to provide a cloud service, a cloud native service, then you need a NIC. Otherwise, you do not need a NIC. We move the BGFS, one of the HPC storage, on this system. You can see in the BGFS, actually, you see no difference compared to the IB device because there's a similar IB. You can see IP address. This IP address is only for labeling. Actually, they have low stack. It's only labeling. Yeah. Then you can see they can do the transportation very well, and you can run the system very well. And especially when you use RDMA protocol with IP labeling, the performance is very good compared to use the TCP. And so more on future. So what we are doing. So when we join the LFH and also Arduino, we always think about the evolution of the networking. So as we said, in nowadays, for the massive cloud, it's only for several big companies like big like ByteDance and also like Amazon. I mean, very few people that can have the ability and also have the money, to build up a massive cloud. Most of the people they only have a small cloud, especially for like only one rack or maybe like 10 racks. So actually, for the networking architecture, we need to think about how to make the connection inside one rack more efficient. I mean, at the most 10 racks, how to scale up in that kind of scenario. So maybe, okay, today we said PCIe is a good Mac. And some people say like Ethernet is a good Mac. Or maybe in the future, like a UALink or CXL link, they will do their own Mac. But it doesn't matter. It doesn't matter what kind of Mac it is. We need to think about how we can put all of them together. And then in the future, for the UEC protocol, like TCP/IP and RDMA, or where is our position? So our position that we want to use the standardized PCIe Mac, like a PCIe controller with a DMA. And then we have adapter to the UEC or RDMA or like a TCP/IP to bring them together and then provide a very efficient and low latency, high performance, and actually most important is a very low cost connection solution to the connection inside a rack. That is our vision and also our thinking on the future like UEC and UALink. So yeah, that's it. Thanks everybody. Yeah.